Hello. Today will be the last lecture on the module eccentric connection. In last few lectures we have seen the design procedure of eccentric connections, where load was lying in the plane of joint, also load is lying on the plane of perpendicular to the plane of joint in both the case, that means in plane loading and out of plane loading. But one case we have not considered, where load is lying perpendicular to the plane of joint, but the connection is welded connections. So, today we will discuss that when a welded joint is under eccentric load and load is perpendicular to that welded joint, then how to design that joint, that will be explained in today's lecture. And you know that joint means welded joint means it will be fillet weld and butt weld. There are two type of weld joint will be. So, that we can calculate the stress develop on the fillet weld and stress develop on the butt weld. In two cases will come into picture, we will discuss two cases. So, let us consider the first case, that is when a column is loaded with the eccentric load, say of E and this P, and this portion is of fillet weld. This portion is fillet weld, means in the plan if we see, this will be like this. Right. So, this will be fillet weld, and then we have to find out the stresses. Stresses means two type of stresses will come into picture in such type of connection. One is shear stress, another is stress due to bending, right. One will be bending and another will be shear, and both will be perpendicular to each other. One will be in this direction, another will be in this direction. So, we have to find out. So, first if we see shear stress means this is due to direct load. Load is coming in this direction. So, shear stress will come. So, this shear stress we can find out in the fillet weld as Q is equal to P by L W into T. So, here L W is the length of weld. Length of weld will be in this case will be, if this is called the length of weld D, then we can find out 2 into D into T, because in this side D and in this side D. So, 2 D into T, neglecting this width which is very small. Okay. So, here P is the applied load with an eccentricity E, and D is the depth of bracket plate or welding depth. So, L W basically is the effective length of the weld, and T means actually T in TT, throat thickness, because strength is calculated on the basis of the throat thickness of the fillet weld. So, T into T, like L W is the effective weld length and T T is the effective throat thickness, right. So, Q, the shear stress, we can find out from this formula, that is P by 2 D into T T, this one. Second is the bending stress. Bending stress we can calculate F B, stress due to bending, that we can calculate that M by I into Y, right. So, if we see the bending stress will develop in this way, and at the center of this it will go. So, this will be tension and this will be compression, right. So, bending stress F B I can find out from this M by I into Y. Now, what is I? I is equal to B D cube by 12, means 1 by 12 into B means T T into D cube, right. This is I of one set, and in other set also it is. So, 2 into 1 by 12 into T T into D cube by D cube, sorry, right. So, I will be basically 1 by 12 2 into 1 by 12 into T t into d cube, and y, this y will be d by 2 because this is d by 2, right. So, if I put this value here m by I into y, then I can find out the f b value as m is p into e by I was 2 into 1 by 12 T t into d cube into t by t. So, if we find out this value, it will be 3 p e by T t into d square, right. So, 3 p e into T t into d square f b. So, resultant stress we can find out, resultant stress will be f e is equal to q square, the shear stress, plus bending stress f b square, right. So, resultant stress in the weld will develop as square root of q square plus f b square, because both are acting perpendicular to each other, and it has to be less than or equal to weld strength. Weld strength means, what will be the weld strength? That will be Fu by root 3 gamma m w, that is the strength of the fillet weld, Fu by root 3 into gamma m w. So, we will calculate the resultant stress, and then we can find out what is the strength, is permissible stress in the weld, and then we can find out whether it is okay or not, right. Now, we will go to design steps. So, how to start the design? Design means basically we have to find out the depth of the weld, that means weld length we have to find out, and we have to assume certain thickness of the weld, that is throat thickness or size of the weld. So, these two things we have to find out. Designing of the weld joint means we have to find out two things. One is effective length of the weld, that is LW, or we can find out the depth of weld, then LW we can find out, LW will be 2 into D, and another is size of the weld from TT, throat thickness, size of the weld. These two we have to find out, but in this case also, as it is not known, so what we can do, we can assume certain size of the weld and we can assume certain depth of the weld. Then we can go and we can check whether it is less than or not, mean permissible stress or not, that we can check, or we can assume certain depth, and on that basis for a particular throat thickness we can find out the shear stress and the bending stress. Then once we find out the shear stress and bending stress, we can make equivalent to the weld strength, and making equivalent to the weld strength, then we can find out what will be the value of T t, the throat thickness, and then what will be the value of the size of the weld, that also we can find out. So, let us start one by one. First we can select a suitable size of the weld. Size of the weld we can find out first, select a suitable size, and then we can find out the throat thickness, and then we can find out the weld strength. Weld strength is basically Fu by root 3 into gamma m w, right. So, first we can find out the size of the weld, means we can assume certain size of the weld, we can find out the throat thickness, and then also we can find out the weld strength. Then in second step what we can do, we can find out the D value. D means depth of weld, that is 3 p e by T t into R w. This is what we found earlier, means earlier from earlier equation we could see that D value can be found. D means the depth of the weld, this portion, right. So, depth of the weld we can approximately calculate. So, this we can calculate, and this depth has been calculated from the moment point of view due to bending moment. Now, also we have shear. So, we have to increase depth D to a certain percent to accommodate the shear stress. So, what we will do, that we will increase the whatever depth is coming, we will increase to a certain amount, so that the shear stress also can be accommodated, because the equivalent stress Fe will be simply q square plus Fb square. Now, on the basis of Fb if we do, then q also has to be taken care. So, therefore, we are increasing depth to accommodate the both the stress. In next step, what we can do, we can find out the direct shear stress, that is q. Q we know, we can find out from P by 2D into dt. From this we can find out, and it has to be less than Rw, right. Rw means what? Rw is the weld strength. So, it has to be less than the weld strength, right. Then we can find out Fb. Fb also has to be less than 3 Pe by Tt into d square, right, and it has to be also less than Rw, means weld strength individually both the component has to be less than Rw, and obviously it will be less than Rw, otherwise you have to increase the size of the weld or we have to increase the depth, right. Next, in next stage we can find out the Fe, which is the equivalent stress due to shear and due to moment. So, due to bending and due to shear, the equivalent stress we will find out, and it has to be less than, the combined force has to be less than the weld strength. So, this is what we can do. If we see if Fe is greater than Rw, then we have to redesign. Redesign means what we will do? We will increase the depth or size, either of these. Depth of the weld can be increased or size of the weld can be increased to ensure the safety of the joint. That means, when Fe will be less than Rw, then it is okay, right. So, unless it is satisfying this criteria, we have to go on increasing the depth of weld or size of weld or both to make sure that design is okay, right. Now, we will go through one example to understand this. This is the example. So, here if we see that a bracket is connected to a column with a 10 mm thick, means thickness of bracket was 10 mm, load is considered as 50 kilonewton at a distance of 150, and depth is given, means 200. Now, design a filler weld, that means here depth is given, you have to find out the size of the weld. Okay. There are three cases will come, either size of the weld is given, you have to find out the depth, or depth is given, you have to find out the size of weld, or depth and size of the weld is not given, nothing is given, you have to find both. So, in case of finding both, we have to go for trial and error, means we have to assume certain size of the weld from the basis of the thickness etc., means minimum size of the weld, and from maximum size of the weld we have to find a suitable size, and then we have to find the depth, and then we have to check. So, both cases can be done, right. So, in this case if we see in plan, this D is given as 200 and this weld we do not know the size, but depth is known. So, if we consider size of the weld as S, then we can find out thickness of the weld as 0.707 S, right. So, now if we find out the shear stress Q. Q will become P by 2 D into Tt. So, by putting the value P is 50 kilonewton by 2 into D, D was given 200 and Tt is basically 0.707 s, right. So, from this we can find out as 176.8 by s MPa. So, shear stress are coming, which is vertical shear stress, are coming 176.8 by s MPa. Now, horizontal shear stress due to bending FB, horizontal shear stress will be how much? That will be 6 m by 2 into Tt into d square. So, that if we find out that 6 into m means P into E, P is 50 into 10 cube, E is 150 by 2 into Tt is 0.707 s into D is 200, so d square. So, after calculation of this we can find out the value as 795.6 by s, 795.6 by s MPa, right. So, FB also we could find out as 795.6 by s MPa. So, Q is found, FB is found. Now, we can find out the equivalent one. So, equivalent one will be Fe will be equal to Q square plus FB square. So, if we put this value 176.8 by s, it is shear stress, vertical shear stress, and this is 795.6 by s is stress due to bending, and if we calculate we will find out 815 by s, and it has to be less than Rw. Rw is the Fu by root 3 gamma mW, that means Fu by root 3 into 1.25, that means 189.37. So, by calculating 815 by s as 189.37, then we can find out the value of s. S will become 4.3, right. So, we can adapt a weld size of 5 mm, because 4.3 mm we cannot provide. So, use S as 5 mm. So, what we have seen in this example, that the depth of weld is given, but size of weld was not known. So, for designing this, what we have found, we have assumed certain size of weld and then we have make equal the external means equivalent stresses due to external forces equal to the weld strength. So, by making equal of this we could find out the size of the weld, right. Now, the second case is groove weld. As I told, there are two cases, one is fillet weld, another is groove weld. So, in case of groove weld, you see here the welding has been done by the grooving in the plate. So, here if we consider the depth of weld as d and thickness as t, then we can find out the shear stress and the bending stress in a similar fashion. you see here Q is P by LW into TE, that means here P by D into TE, not 2D. In earlier case what we have seen, earlier case we have considered 2D, because in two places, in two sides periphery, in periphery the weld joint has been done by fillet weld, but in case of group weld this will be only D. So, Q we can find out from this formula, that is P by D into TE. Similarly, the FB, the stress due to bending, I can find out as M by I into Y, where I is equal to 1 by 12 into TE into D cube. Here remember that T is the effective thickness of the group weld, right, and Y is equal to D by 2. So, in a similar fashion, if we provide, means if we put the value of M by I into Y, where M is equal to P E into E and I is equal to 1 by 12 into T E into D cube and Y as D by 2, then we can find out F B as 6 P E by T E into D square, F B as 6 P E into T E by D square. You can remember that in case of fillet weld it was 3 P E by T into D square, T T into D square, right, and resultant stresses for group weld we know that F E is equal to square root of 3 Q square plus F B square, and it has to be less than F Y by gamma m 0, where F Y is the yield strength, right, not the ultimate strength. So, resultant strength we can find out resultant stress as F E, that is root over 3 Q square plus F B square, and it has to be less than F Y by gamma m 0. We can calculate the equivalent stress. Now, coming to the design steps. So, for designing of group weld, if we see in a similar way we can move forward, that is first we can select a size of the weld, suitable size of the weld, and then we can compute the effective thickness. Effective thickness of the group weld can be found from the thickness of the member. Means if two plates are joined together, then from the thickness of the member, thickness of the thinner plate, or in what way it is connected we have to see, from that we can find out the group weld thickness, and also whether it is fully grouped or partially grouped, that also we have to see, and then we can find out the thickness of the weld, and then we can find out weld strength also. Weld strength is basically R W, here will be F Y by gamma m 0, gamma 0. Okay. So, sorry, this will be gamma m 0, F Y by gamma m 0. Now, we can calculate the depth of weld using expression D is equal to this square root of 6 P E by T E into R W. Earlier we used 3 P E in case of fillet weld. So, please remember this difference. Now, D we can find out, again this D also can be increased to a certain amount to accommodate both the stresses, then we can find out the actual stress coming in the weld, that is Q is equal to P by D into T E, right, and it should be less than obviously R W. If it is not, then we have to increase the size of the weld or depth, and similarly we can go for calculation of the bending stress. So, bending stress also we can find out from this formula, that is F B is equal to 6 P E by T E into D square. So, and that also has to be less than R W, and then we can find out the equivalent stress. Equivalent stress will be square root of 3 Q square plus F B square, and that this equivalent stress has to be less than R W. So, now if the equivalent stress exceeds the design weld strength, then the length of weld should be increased and above process be repeated till the checks are satisfied, which is as usual. That means, if the design strength is less than the equivalent strength, or in other way if we see the equivalent strength is coming more than the permissible stress, then we have to redesign. Redesign means we have to increase the weld length or weld depth or weld thickness. Then again we have to redesign and we have to check whether it is okay or not. If it is not okay, again we have to go for the same steps. Now, the same example which has been considered earlier will be done using the group weld, right. Here if you see, the example is exactly same, that 150 means 50 kilonewton load is provided with 150 depth and same sort of bracket plate, that is 10 thick bracket plate, and also the depth is given, that is 200 depth is given. So, the example which we have done earlier, the same example has been considered, and in this case only difference is that we are using group weld. So, if we use group weld, how to design the connection, that we will see. So, here we can assume single or double group weld. So, for example, in this case we have considered the double J group weld. So, as it is double J group weld, so what will happen means effective throat thickness will be the thickness of the bracket. So, in this case thickness of the bracket is 10 right. So, as it is a double J group weld, so the thickness means effective thickness of the group weld also will be 10 So, if this is 10 then vertical shear stress we can find out, that Q is equal to P by D into TE. So, vertical shear stress we are getting 25 MPa. Again the horizontal shear stress due to bending FB we can find out, that is 6 m by TE into D square. If we put the value of individual parameters like 6 into m means 50 into 150 by TE is 10 and 200 is D. So, if we put those value, we will get the horizontal shear stress due to bending as 112.5 MPa. So, what we see, the vertical shear stress we are getting this and horizontal shear stress we are getting this, and of course, we have to see what is the permissible stress. Permissible stress is Fy by gamma m0, right. Permissible shear stress we can find out Fy by gamma m0, that is 250 by 1.1. So, that is 227.27 MPa, which is more than the individual stress due to shear stress and bending. Okay. Now, the resultant stress at the extreme fiber will be square root of 3q square plus fb square. Now, if we put this value, q was coming 25 and fb was coming 112. So, the resultant is coming 120.55, right. So, if we put this means if we find the equivalent strength, then we could see that the equivalent stress is much less than the weld strength. So, the resultant stress is less than the weld strength, that means the joint is safe, right. So, in this way we can design, that means here what was given, the length of weld was fixed, length of weld or depth of weld was fixed, and the thickness is also fixed because it was a double J groove weld, and so the effective thickness was also fixed. So, what we need to do here is the equivalent stress we have to find out, and that equivalent stress whether it is less than the strength permissible strength or not, that we have to check. If it is okay, then fine, if it is not okay, then design is not safe. However, if the depth is not given, then we can find out the depth also by trial and error method. The way we have discussed earlier, in the same method we will find out the approximate depth and then we can check whether it is okay or not. If it is requirement is means the equivalent stress is much less than the weld strength, then we have to decrease the depth and we have to check again, and if equivalent stress is more than the permissible stress, then we have to increase the depth of the weld so that we can accommodate it. So, this is how we can find out the design strength of weld, and we can find out the equivalent stress of the weld, and we can check. So, in last few lectures we have discussed the eccentric connections, and in eccentric connections two type of connections will come. Basically, one is due to in plane loading, another is due to out of plane loading. In case of in plane loading, we have seen what are the stresses will develop and how to design, and in case of out of plane loading also we have seen what are the stresses are coming and what are the equivalent stress and how to design, right. And we could see here in all the cases the design procedure is basically a trial and error method. We will assume certain parameters, then we can find out the stresses developed on the joint, whether it is bolt joint or weld joint, whether it is butt weld or fillet weld, and then we have to see whether it is exceeding the permissible limit or not. If it is not exceeding the permitted limit, then design is fine, otherwise we have to redesign with the increase of number of bolts, diameter of bolts or weld thickness, weld depth, etc., as per the case required. So, this is how we will do. So, with this I would like to conclude the entire lecture of eccentric connections. In next class we will discuss about the design of tension member. Thank you.